Thank you all for coming. So we'll continue where we stopped yesterday with tying up one loose end about the action of the right-angled Artin group on its extension graph. Let me remind you again what the extension graph is. So the vertices are conjugates of vertices of the defining graph. And the edges are given by pairs. So recall that we're trying to build an analogy with the mapping class group action on the curve graph. And one thing that I'd like to sort of talk about that I didn't get to last time is the boundary action. So there's a well-studied action of the mapping class group on the space of projective measured laminations of a surface. So if you don't know what these are, this isn't that important. But the point is that this is naturally identified with the boundary of the Teichmuller space of the surface S. And in general, this action is quite complicated. But pseudo-Anosov elements have a nice property. So pseudo-Anosov elements classes have north-south dynamics. Which is to say that a pseudo-Anosov mapping class has two fixed points which are distinct from each other, which you can think of as the north and the south pole. So P1 and P2 are exactly the fixed point set of a pseudo-Anosov psi. And outside of a neighborhood of these two, psi moves points a definite distance towards P1, say, so one of these two. So it moves everything away from P2 and everything towards P1. Furthermore, there's this two pseudo-Anosovs which don't generate cyclic subgroups have different fixed point subsets. So if psi1 and psi2 are pseudo-Anosov, and we have that the subgroup generated by psi1 and psi2 is not virtually Z, then the fixed point set of psi1 and the fixed point set of psi2 are disjoint. Oops. So from the point of view of dynamics, this is a very useful setup. And what this allows us to do is play ping pong. So if, let's say we'll have P1 and P2 are the fixed points of psi1, and Q1 and Q2 are the fixed points of psi2, then what we can do is we can choose fixed neighborhoods of P1, P2, and of Q1, Q2. So I'll call these two together capital U, and these two together are capital V. So what the north-south dynamics of pseudo-Anosovs on PML says is that for all n sufficiently large, we have that psi to the plus or minus psi1 to the plus or minus n applied to V sits inside of U, and furthermore, if you switch the roles of psi1 and psi2 and of V and U, we have these inclusions. And so what this implies is that if that for all n sufficiently large, we have that the group generated by psi1 to the n and psi2 to the n is free on two generators. Now, we can almost play the same game on the boundary of the curve graph. The boundary of the curve graph is not the space of projective measured laminations, but it's something very close. So what the boundary of the curve graph is a space of ending laminations on S, which is identified with a subset of the projective measured laminations after forgetting the measure. And this equality is established by a theorem of Clari. And so what one can show is that the action that if psi, a mapping class, is pseudo-Anosov, then the action of psi on the ending laminations is by north-south dynamics. And if psi1 and psi2 are incommensurable. So what I mean by incommensurable, I mean that the subgroup they generate is not virtually cyclic. Then fix psi1. Okay, and so the same sort of ping-pong argument works. So the way I've sort of illustrated north-south dynamics, it actually looks like we're doing some sort of dynamics on a sphere, and in the case of the mapping class group action on the space of projective measured laminations, the space is actually a sphere, and so you can almost think of it as like a flow from the north pole to the south pole. So the pseudo-Anosov mapping class is like a lattice inside of a flow or something like that. But the topology of the space of ending laminations is much more complicated, but we still have the same conclusion. So now recall that we had this theorem from last time that if gamma is connected, then the extension graph, gamma E, is a quasi-tree. And what follows from this is that the boundary of the extension graph is either completely disconnected or it's empty. So when I say it's completely disconnected, it's also perfect. So it's like a Cantor set, but it's not actually a Cantor set because it's not compact. And this case happens exactly when the diameter of the extension graph is finite, or it's actually when it's less than or equal to 2, which is if and only if gamma is a join. And so now the analogous theorem to the mapping class group action is that if lambda in A of gamma is loxodromic, then lambda acts on the boundary of the extension graph by north-south dynamics. And we have the non-commensurability fact. So if lambda 1 and lambda 2 are non-commensurable, then fix lambda 1. And so, as a consequence, we have this sort of ping-pong arguments which work on the boundary of the extension graph as well. And so note also in particular that we don't have any boundary exactly when the extension graph is finite diameter, which is exactly when the graph itself is a join. And in this case, there are no loxodromic elements. And so then this is still vacuously true, even in that case. So I alluded to this deep result here of Clareich, which gives a topological interpretation to the boundary of the curve graph, which is very important for proving many results about the curve graph itself and about even hyperbolic three manifolds in a quite non-obvious way. The interpretation of the boundary of the extension graph is not clear at all. So what is the boundary of the extension graph? It's sort of an open question. We don't have a very good understanding of what those elements are supposed to mean. Okay. So now that we have this dictionary of results between the mapping class group and the right-angled Artin group, I'd like to understand the geometry of the extension graph in a deeper fashion, and show that is also very much related to the geometry of the curve graph. So first we can talk about distances in the extension graph. So a general question that one might pose is is if you take some element in the extension graph, some element in the right-angled Artin group, and some vertex of the extension graph, and you consider the distance between V and its conjugate by G. And you might wonder, what is this? I mean, so we've defined some graph, and so it has some natural graph metric. And in particular, you might ask, rather than precise questions of what is this distance, sort of have an idea of when is this distance large? So I mentioned a theorem that says that if G is loxodromic, then this distance can be very big. It can be as big as you want it to be. But how do we understand this sort of largeness? It doesn't have anything to do necessarily with the length of G as a word in the right-angled Artin group, because if G were, say, just V to some power, then G and V would commute with each other, and so this distance would be 0. So there has to be something somewhat deeper going on. And the answer is sort of general. So it turns out that this distance is asymptotically. So what I mean by this symbol is that there is some fixed, which depends only on gamma, multiplicative and additive error. This depends on something called the star length of G. So what this means is that we can write G as a product of other words in the right-angled Artin group. Here UI is in the subgroup generated by the star of some vertex V. So here V is a vertex of gamma. And then the star length of G is the minimal such n. So this is since vertices themselves are supported in subgroups generated by stars of vertices, then this star length is at most the word length, and in general it's much smaller. And so this theorem, this is sort of this is a theorem which is equivalent to some relation between the extension graph and the Cayley graph of the right-angled Artin group. So I'm going to take X to be the Cayley graph of A of gamma. It doesn't matter which generating set I choose. And what I'm going to do is I'm going to construct an electrified Cayley graph. So what this means is I'm going to essentially make all of these star subgroups uniformly finite diameter. So this is going to be equal to the Cayley graph union the cone on the cone on the centralizer of a vertex inside of the right-angled Artin group itself. But this is unfortunately not good enough. We also have to take all the cosets. So the centralizer of a vertex V, this is a subgroup of the right-angled Artin group, and it's precisely spanned by the star of V. And so what I'm doing is I have, the Cayley graph X, and then I'm taking a vertex V and I look at its centralizer inside of the right-angled Artin group. And then I attach a cone point. So, and I join this cone point to every vertex in this subgraph. I declare each of these edges to have length 1/2 or something like that. And so what it turns out then is that the electrified Cayley graph is quasi-isometric to the extension graph. And this is analogous to a certain construction inside of the mapping class group, which relates the Cayley graph of the mapping class group to the curve graph. So if here we write X for the Cayley graph of the mapping class group of S, and we write X electrified for the electrified Cayley graph where we cone off centralizers of Dane twists. Then it turns out that this electrified graph is isomorphic to, is quasi-isometric, not isomorphic, to the curve graph of S. So this is one way in which one can understand distances inside of the extension graph. And this is important for the next construction that we want to do, which we hope at least deepens the understanding of the extension graph. So the inspiration comes from Mazur-Minsky's subsurface projections, which allow one to understand the local geometry of the extension graph, of the curve graph. So suppose we take a subsurface X. Here, X is going to be essential and incompressible. And let's suppose that gamma is a vertex of the curve graph of S. And so a schematic picture may be something like this. So here's S, and X is this torus with one boundary component, and then gamma is some curve which may or may not intersect X. And so what subsurface projection is supposed to do is it takes a curve gamma and gives you an approximation of what it looks like on the subsurface X. And so precisely what one does, I'm going to abuse notation, and I'm going to write pi of X for the subsurface projection map. And this takes the curve graph of S, and it associates, I'm going to write that it maps from the curve graph of S to the curve graph of X, but that's strictly not true. What it does is it associates a possibly empty multicurve inside of X. to each vertex of the curved graph of S. So the way this is defined is that if gamma intersect x is empty, then pi x of gamma is empty. And otherwise, we look at a tubular neighborhood of gamma intersect x union the boundary of x, and then we take the boundary of this, and this is defined to be projection onto x of gamma. Okay. And so the reason why we want to consider this sort of construction will become clear a little bit later, but suffice it to say that we want to have a similar construction in the theory of right-angled Artin groups. Now the problem is that we don't have any subsurfaces lying around in any natural way, and so we have to think about subsurface projection in a different way. And there's a particular specialization of subsurface projection which allows us to mimic the construction in the right-angled Artin group case. So I'm going to consider a very particular situation. So suppose V on S is a simple closed curve. Then we can look at S without V, and we're going to think of this as X. And now, clearly the curve graph of X includes into the curve graph of S. But there's a better description of just this inclusion rather than just thinking of it as an inclusion of graphs given by an inclusion of surfaces. One can think of the curve graph of X as naturally identified with the link in the curve graph of S of V, because the non-peripheral curves of X are precisely the curves on S which are disjoint from V. And so what Mazur and Minsky observed is that so you can do the following construction. So you can have V, this vertex inside of the curve graph, and you can consider some very, very far off vertex gamma. And you can graph theoretically say what it means to approximate gamma by curves on X, namely S minus V. And there's a canonical way to do it graph theoretically. You consider all the geodesic segments connecting gamma and V. So you have T gamma V, this is the set of geodesics between V and gamma. And then if you want to say, well, you can think of this construction as sort of a visual direction. You stand at V and then you look at gamma, and the curves that look most like gamma are the ones which you encounter first on a geodesic traversing from V to gamma. And so what you can do is you can define pi x of gamma to be T gamma V intersect the link of V. So I'll write this as pi prime. What this theorem that Mazur and Minsky proved is that, first of all, pi prime x of gamma is well defined, which really it's coarsely well defined. So what that means is that the diameter of the set is bounded independently of v, gamma, and x. And secondly, they showed that the distance in the curved graph of x between pi x of gamma and pi prime x of gamma is uniformly bounded. And so up to a finite amount of error, you may as well define the projection of gamma onto the subsurface x to be this intersection, the intersection of this set of geodesics with the link of v. And so because this is a completely graph theoretic construction, we can understand it or completely mimic it in the case of the extension graph. And so in our case, we have vertex link projection. So first we have a construction that can be done in general. So we start with a vertex v in a graph, and we have some other vertex v prime. And we'll assume that this graph is connected, so there exists at least one geodesic segment between v and v prime. So we have t v prime is the set of geodesics. Connecting v and v prime. And so the vertex link projection of v prime onto v is defined to be the intersection of t v prime with the link of v. So this is going to be the basis of vertex link projection for right-angled Artin groups. We want to be able to say something like this Mazur-Minsky theorem, like that the diameter of the set is uniformly bounded or something like that. There's an issue which arises in that so when we say that the diameter is bounded independently of v, gamma, and x, there has to be some sort of metric that we're talking about. And what is that metric? Well, here we said that the metric is in the curved graph of x. And so when we're talking about distances in the link, we have to have some sort of metric on the link which makes sense. If we just consider the inherited metric from the extension graph, then the link sits inside of the star of some vertex v, and so saying that this set has bounded diameter has no content to it. And so there has to be a metric on the link which makes sense. So that's where the discussion of star length becomes of crucial importance. So suppose so actually, let me state one sort of fact first. So an important lemma that will allow us to pass between the graph and its extension graph more easily is that there is a canonical identification between the link in the extension graph of V with the link in gamma of V extension graph for all vertices of gamma. So taking an extension graph commutes with taking links in some sense. And so let's think about what the link of a vertex might be like. So suppose
this is the whole vertex in gamma or gamma E?
I'm going to say in vertices of gamma, because otherwise the link in gamma of the vertex doesn't quite make sense. It's true that every vertex of gamma E is conjugate into a vertex of gamma, and so you may as well pretend that that vertex was already in gamma. So if you suppose that gamma is triangle free, then the link of each vertex is completely disconnected. And so, in particular, the link in gamma E of V is generally just a completely disconnected set with infinitely many vertices. It may just consist of one vertex if V had degree exactly 1, but in general it's going to be like that. And so it takes some care to understand how we're supposed to think of this set as a metric space. So of course one could think of many different metrics on this, but there's a natural one. And so we can identify the group generated by the link of V in gamma with a free group on some number of vertices, so some number of generators K. And so then the vertices of the link in gamma E of V are in bijective correspondence with conjugates of free generators for Fk, so a particular fixed set of free generators for Fk. And so we can consider a free generator V and a conjugate by some element in Fk and think about what this distance is. Well, we already had that in the connected case. This distance was roughly just the star length of G. And so what we define this distance up to some bounded multiplicative and additive error, which we don't really care about that much, to be the star length of G in this free group. So what is the star length in a free group? Well, if you consider what the links of vertices in a completely disconnected graph are, if the star of any vertex V is just equal to V if V is isolated. And so if we had a word, say, W, which is A to the N1, B to the M1, all the way to A to the NK, B to the NK, where these NI's are not equal to 0, and this is some word in the free group on A and B, then the star length is just the number of alternations between A's and B's, and so this is it's like 2k minus 1 up with an error of at most 2. And so this is how we're going to define the distance on the link. And so given this definition, it's possible to state a well-definedness theorem about this vertex link projection. So suppose gamma is triangle free, and for technical reasons we also need it to be square free. Then the operator vertex link projection to V is well defined. Of course, when I say well defined, I mean coarsely well defined. So in particular, if I have any vertex V prime, then the diameter in the link inside of gamma E of V of the intersection between the set of geodesics connecting V and V prime with the link of V is uniformly bounded independently of V and V prime. And so one can easily construct examples where this is not true. So, I mean, this is not a vacuous statement about graphs. This is really something specific to right-angled Artin groups and their extension graphs. Okay, so what's the point of subsurface and vertex link projection? Well, there's this very important theorem of Mazur and Minsky, which is known as the bounded geodesic image theorem. And so what the bounded geodesic image theorem does is it allows us to give some sort of quantitative meaning to visual direction within the curve graph. So the curve graph is just a combinatorial object, and so measuring angles and stuff like that doesn't make any sense. And talking about some sort of visual metric on the boundary also doesn't make any sense. But what the bounded geodesic image theorem is supposed to do is it's supposed to give some rigorous meaning to the idea, to an idea that really comes from hyperbolic geometry. So if you have hyperbolic space like this, and you have some geodesic gamma, and then you have some other geodesic which does not encounter gamma. So there's a natural way to project delta onto gamma. You take the nearest point projection, so you just drop a geodesic from delta to gamma, which hits gamma at a right angle. And so this projection, so this nearest point projection sends delta to a bounded subset of gamma. And the diameter of that subset depends on the distance between these two geodesics. So what the bounded geodesic image theorem says precisely is that we take X a subsurface, so it should be essential and incompressible. And gamma inside of the curve graph is a geodesic. It could be finite, it could be semi-infinite, it could be bi-infinite. And we assume that if gamma is a vertex of, if C is a vertex of gamma, then C intersects X essentially. Then the diameter of the projection onto X of gamma is uniformly bounded independently of X and gamma. So I'll state the corresponding theorem in the extension graph case and sort of illustrate why you need this technical assumption here. So let V be a vertex of gamma E, and gamma a geodesic, such that gamma intersect the link of V is empty. So we avoid the link of V. Then the projection onto V of gamma is uniformly bounded by a constant which depends only on gamma. Furthermore, if X is a subset of gamma E, which is connected, and X avoids the closed ball of radius 2 about V. So it avoids not only the link of V, but the link of every vertex in the link of V. Then the projection onto V of X is uniformly bounded. So I just wanted to draw one sort of schematic picture. So why do we need this condition that we avoid the link? Similarly, why do we need this condition that each vertex on that geodesic intersects the projecting subsurface X, essentially? And the idea is this. So suppose that you consider this the vertex V here, and here's its link. So what the bounded geodesic image theorem says is that if you have some geodesic that's going between 2 points, or maybe it's by infinite, and you project it onto the link of V, then you get this bounded diameter projection. However, if you had some geodesic which, say, passed through V and then went on its way, then it's possible that you can when this link is completely disconnected, that you could essentially, that once a geodesic has reached this point in the link, you can continue on to V and then continue on to any other vertex in the link, and the resulting segment would also be a geodesic. And so the distance between these points can be arbitrarily big. And so that's why one needs this assumption that gamma avoids the link of V, because otherwise the theorem would be incorrect. Okay, so in the last 10 minutes, I'd like to talk about the usefulness of the bounded geodesic image theorem in understanding the mapping class group. And similarly, it's the use of the bounded geodesic image theorem in the right-angled Artin group case in understanding something about the right-angled Artin group. Okay, so what Mazur and Minsky proved is a distance formula, and the objective of this distance formula is to coarsely recover the metric on the Cayley graph of the mapping class group. So the issue being that the mapping class group is an extremely complicated group, and understanding the geometry of its Cayley graph is quite difficult. So the idea of the distance formula is to first build a combinatorial model for the mapping class group. That is something which is more amenable to study through the curve graph than just the Cayley graph with its word metric. So the answer to this problem of building such a combinatorial model is answered by the marking graph. So the vertices of the marking graph are collections of simple closed curves which, in some sense, I'm not going to give precise definitions of this because it would take too much time. They bind the surface so that they fill it up completely and satisfy certain minimality properties. And then adjacency in this marking graph. Adjacency is given by some sort of elementary moves. And so what Mazur-Minsky showed is that this marking graph is actually quasi-isometric to the mapping class group. So the large-scale geometry of this graph that's built out of these collections of simple closed curves is indistinguishable from the mapping class group. And so now, if you have a subsurface X, you can consider the projection onto X of a marking. So you forget that this marking had any of these properties, that it bound the surface or that there were some sort of minimality conditions, just that it's a union of simple closed curves. And then you can consider the projection onto a subsurface by, this is just the union over the components of mu of the projection onto X of the components. And so what it turns out is that the diameter of pi of X of mu is at most, it's at most 2, certainly. I think it's actually at most 1. No, it's 2, sorry. So the distance formula says that if you consider the sum of the distances in the curve graph of S between the projection onto X of 2 different markings. So you want this to be something like the distance between mu1 and mu2 inside of the marking graph, but this is not exactly true. One has to take a truncated sum. So I'll explain what this means. So this star means that means only include summands which are sufficiently large. So precisely, there exists a constant so that if you take the sum of these projections over all possible subsurfaces for which this projection is larger than that constant, then you coarsely recover the distance between the 2 markings in the marking graph. So what this theorem does is it relates the geometry of the curve graph, which forgets a lot of information about the mapping class group since it's this coning off of all these Dane-twist centralizers, relates it to the geometry of the mapping class group in this very precise way. So the distance formula for right-angled Artin groups is a little bit less neat due to the fact that some of the technology that's used in establishing this distance formula is lacking in the extension graph case. And also there's this problem that the extension graph is much too symmetric for something, for a formula which is as nice as this one to possibly hold. And so what the distance formula for a right-angled Artin group will recover is the syllable length. So the syllable length of a word G is defined as follows. So you write it as a product of vertices taken to certain powers, and you take the minimal k over all such expressions. And so I'll just state one example of a distance formula in sort of its nicest case, namely in the case where the original graph was a tree. So let gamma, this is a theorem, So let gamma be a tree with diameter at least 5. We need this assumption for technical reasons. So there exists a V in the vertex set of gamma such that for all G in the right-angled Artin group, the sum over all vertices in the extension graph of the distance in the link of V prime between the projection onto V prime of V and the projection onto V prime of V to the G. This is coarsely approximating the syllable length of G, where this additive and multiplicative error depend only on the graph gamma and not on little g or v. Okay, so I think this is a good place to stop.